continue with lecture 3 by Cosmological.
All right. So, in the first couple lectures, we discussed eigenstate thermalization and how we expect it to show up in two-dimensional CFTs. And as I emphasized at the end of the last lecture, that was a discussion about individual CFTs. That a particular CFT would behave as if, well, the ETH ansatz that needs to be checked is that a particular CFT would behave as if the OP coefficients were determined by, well, you determine their average by Tauberian or Bootstrap methods, and then they're as random as possible subject to the constraints of that Bootstrap analysis. But now, as I explained at the end last time, we're now going to discuss averaging over those coefficients. In order to be concrete here, I want to define a particular ensemble of large C CFTs. The reason for taking large C is to make it holographic, or at least plausibly holographic, and now we need to check if it agrees with 3D gravity. So the ensemble that we're going to consider is the following. The spectrum consists of a vacuum state, defect operators, which are operators whose weights lie between C over 32 and C over 24. Remember that in the semi-classical limit, we like to parameterize the weights in terms of eta, which is related to the defect angle of the dual particle in ADS3. C over 24 here is the black hole threshold. The reason I'm requiring it to be heavier than C over 32, this isn't really necessary for most of what I'm going to say, but the reason I'm imposing this is to avoid having multi-twist states. So in Virasoro mean field theory, as we talked about yesterday, if you have light operators in a 2D CFT, then you get composites, like in higher dimensions. But if they're heavy enough, then there's no discrete set of composites. There's only a continuum black holes. Okay, so we have some finite list of defect operators, and then we have black holes. The black holes are the states with H greater than C over 24, and we'll assume that the density of states of those black holes is given by Carty, which I'll denote by rho 0. So rho 0 is the Carty density of states. That's the spectrum. In order to finish defining this ensemble, we also have to define the OP coefficients, or the statistics of the OP coefficients. So we're going to treat the OP coefficients as independent random variables, independent Gaussian random variables. This is just an approximation. It needs to be corrected as I'll explain. But the leading term, the starting point here is that the average of C and C star is given by the Tauberian result, which is a smooth function of the weights, the contraction. There are permutations coming from the permutations of the permutation symmetry of these indices, and there can be subleading terms that we don't fully understand, but some of these terms I'll talk about.
Sorry, just curious about how this number is obtained.
How, what number?
The number like 1 over 32 over 24.
Yeah.
Is a big factor of that.
Yeah, that number is that number ensures that the etas always add up to something above the black hole threshold. So remember in Virasoro mean field theory, it's the etas that add, defect angles add, and that's where the 32 comes in. Okay. Now this data should be viewed as like a leading order input if you're familiar with topological recursion and random matrix theory, then philosophically you should think of this as being similar to the genus zero data. There's not literally a one-to-one match. It's a topological recursion, but that's the idea. This is the leading order data, and you're supposed to take this and plug it in and solve consistency conditions order by order, bootstrap conditions, in order to correct it to solve crossing to better and better accuracy. We don't know systematically how to do that, but there are at least some of the equations we know how to solve. The last thing I want to remind you of is that this C0 is equal to the structure constant of the Liouville CFT up to some factors of the density of states. Okay, so why are we doing this average? Well, to motivate this, I want to turn to holography and some work that's been done over the last few years. So a really interesting development recently is that two-dimensional JT gravity is holographically dual to random matrix theory. So this is a duality, SSS duality for its authors. Now, in this duality, the random matrix of random matrix theory is the Hamiltonian. Since it's two-dimensional gravity, the boundary theory is 0 plus one-dimensional quantum mechanics. And in quantum mechanics is sort of anything goes. You know, if I just give you a list of numbers, any numbers I like, I can declare that to be the spectrum of a quantum mechanical system, and you can't stop me. That's fine. Like I can just put those on the diagonal of my Hamiltonian, and declare that to be my Hamiltonian, and that's quantum mechanics. Of course, in higher dimensions, something has to be fundamentally different. You know, it can't be that higher dimensions has just random Hamiltonians, because we know from locality, from the Bootstrap, that higher dimensional quantum field theories have to satisfy all sorts of consistency conditions. You can't just write down a spectrum and declare it to be the answer. So something has to be fundamentally different in higher dimensions, and that was part of that's part of what we're trying to understand is how can we do something similar in higher dimensions? On the one hand, it should be random in some way, but on the other hand, it has to satisfy the Bootstrap constraints. And this example in two-dimensional gravity is especially interesting because it seems to be fundamentally different in some ways from the usual examples of ADS CFT that we like to talk about. In particular, random matrix theory is not quantum mechanics anymore. Okay, I just said it's quantum mechanics. It's an ensemble of quantum mechanical theories. And an ensemble of quantum mechanical theories is not a quantum mechanical theory. In particular, there are contributions to JT gravity which have two boundaries. So this is a picture of a two-dimensional geometry. It's a Euclidean geometry with two boundaries. So this contributes by the ADS CFT dictionary to a product of two thermal partition functions in the dual boundary theory. Now, in quantum mechanics, the partition function is just a number. It's some and two copies of the partition function are just a number times a number. So in ordinary quantum mechanics, this obviously has to factorize, but in JT gravity, it does not. So this is known as the factorization puzzle, and the way that this puzzle is resolved or explained in the SSS duality is that since it's actually an ensemble of quantum mechanical theories, there's some averaging going on the right-hand side, and that averaging introduces correlations between the two copies of the theory, and now it's perfectly acceptable for them to be correlated. So that's what we're trying to understand. We're trying to understand when the bulk theory, when the gravitational theory has non-factorizing connected contributions like this, what do they mean from the point of view of the boundary theory? That's what we're trying to understand. And in higher dimensions, it has to be something a bit different. We think that it should be telling us something about some kind of average quantity in the boundary, and we want to understand what that is. Okay. So,
Can I ask a question?
yeah, go ahead.
In general, you mentioned the most naive solution to the factorization, something like let's just not include among the samples you want to compute.
Sorry, does not include what?
Let's just not include any sample which does not factorize, any connected sample. Does it run into immediate contradiction? Is it known to fail? Can we just define immediate gravity?
Good. No. Yeah. That was, I think, the lore. That was kind of the standard proposal until recently, was that, well, we don't really know how to do gravitational path integrals, so we don't really know what kind of saddles to include. And if we see something that violates the axioms of quantum mechanics, that must mean that we don't include it. Okay, so that was what people said for a long time. We should just drop them. But I think what we learned from this duality is that that's too quick. That these saddles are telling us something interesting. Now, maybe in UV complete theories, if you analyze it exactly, they actually cancel or drop out for some reason. But even if that's true, they seem to be telling us something interesting, something about some average quantities, so we should figure out what they're telling us. I think that's how I think about it. But yes, they could be canceled or not contribute at all in a particular exact CFT.
Can I ask something more precise about this? So, for instance, if I just don't know if they cancel, but I just don't include them, do I contradict computations where they are needed? It's, for instance, replica wormholes for entanglement entropy, or not, because they're like connected or something like that? Can I have replica wormholes, but
strictly speaking, no. Strictly speaking, no. So like replica wormholes are not required to factorize, because replica wormholes have some gluing going on between the boundaries, and then the wormhole grows between two things that are supposed to be correlated, and then they are correlated, so it's okay. But there are wormholes that are extremely similar to replica wormholes, so it would feel a little weird to include the replica wormholes and not the very similar ones which have a factorization paradox. There isn't a strict problem with dropping them, but it feels uncomfortable.
Okay, there's no one parameter family that connects a solution. Like, say I made in these double holographic models, I made a boundary not transparent anymore. I kill the gluing, and
I think you'll kill the replica wormhole if you take that parameter to 0.
Okay.
Yeah. But what you can do is the way the replica wormholes, or one way to get replica wormholes is to put twist operators on the boundary that glue these together. And the weird thing is that if you replace those twist operators by local operators, then the bulk theory doesn't care. It'll still give you a wormhole. But now you have a factorization problem. So they're very similar solutions. From bulk point of view, it's weird to include one and not the other. But maybe that's the way it works.
Okay.
Sorry, I have a question. So this sort of factorization problem, does it only exist above some threshold or of energy?
So in 2D gravity, there's not a threshold for black holes? Is that what you have in mind? Like a black hole threshold,
Yeah,
like we
yeah.
have for BTZ? No. So maybe I should have emphasized that this is not a saddle. Okay. So, and this will be a difference from what I'm going to talk about in 3 dimensions. This is an off-shell gravitational path integral. Now in JT gravity, it's under enough control that you can do that path integral. So there's no threshold, contributes everywhere, but you could do that path integral and you get some contribution that's non-zero, and that's what's compared to random matrix theory. Okay, so the first thing that I want to explain is how it makes sense at all in terms of Bootstrap to use this ensemble. Now we've already talked about the 4-point function, and one consequence of what we talked about yesterday is that the 4-point function is crossing invariant on average. What I'm going to explain now is how more complicated observables in this ensemble are crossing invariant. Not exactly, but on average. So there's one example that I think illustrates this nicely, which is the 6-point function. So let's look at a 6-point function of the operators O1, O2, O3, O3, O2, O1. So these are equal in pairs, and in the bulk, so if we calculate this in ES3 gravity, I'm going to take these to be defect operators. So this is a 6-point function of 6 defect operators. So in the bulk, this calculation is a gravitational saddle that looks like, I'm going to do this in Euclidean, so there's a H3, and that H3 has 3 defects running through it. These are 3 different flavors, so they can only combine with their partners. So there's a defect of type 1, there's a defect of type 2, and there's a defect of type 3. Okay, so that's the gravitational saddle that calculates this 6-point function.
So just to be clear, so you call them defects because they are conical defects in the bulk?
That's right.
But from the boundary perspective, they're just local operators?
Yes, exactly. They're just local operators in the boundary. They're just heavy particles in the bulk, which are heavy enough to back react in a 3D gravity that makes a conical deficit. So in the bulk, to calculate this 6-point function, what you're supposed to do is you're supposed to calculate e to the minus the on-shell action of this solution. And there's a general story that the gravitational action in cases like this is given by a Virasoro identity block. So in this case, this is the Virasoro identity block. Well, basically, anytime if say I draw a loop around operators 1 and 2 on the boundary. So that loop is drawn on the boundary sphere. Now, in the bulk geometry, I can contract that loop. It's homotopically trivial. I can contract that loop to nothing by bringing it in around the defects. And in gravitational solutions like that, that tells you that it's a Virasoro identity block with the identity operator running in that OPE contraction. Now we could do that for any of these pairs. So what that tells you is that there's an identity block that looks like this. And that's the chiral, if we view that as the chiral Virasoro block, we have to take the antichiral part, so I'll put a mod square. Okay, so this is a relationship between gravitational saddles and Virasoro identity blocks. This one I will call F star for the identity operator mod square. So there's some particular channel. The channel is determined by what you can contract in the bulk, and this is the relationship. from a CFT point of view, the reason that this 6-point function is given by the identity block is because we've assumed that the theory has no other light operators. Just has the identity is the only light operator. Well, I'm assuming that the defect operators don't interact with each other. So the identity is the only operator that can run this OPE. So that's the leading approximation to this 6-point function. Okay, so that story is sort of an old one.
Can I ask a question? So on the gravity side, how do you describe this defect operator?
It's just a massive particle. It's just a massive particle.
So in the gravitational action, so what are the terms which are something?
Yeah, let me write the gravitational action. So the bulk action that we'll be comparing to throughout the lecture is the Einstein action plus a sum over the defects of the defect weight times the GD's, the world line action of the defect. Up to various constants that I'm dropping here. Okay, so that's sort of an old story. But now I want to reinterpret it in terms of this ensemble average language. So in the ensemble average, we should be able to compare this to other channels. So we should be able to calculate, we should be able to check this as a bootstrap equation. So let's compare it to the cone channel. So the cone channel is this one. 1, 2, 3, 3, 2, 1. So those, this is the 6-point function again. And now we have 3 internal weights, I, j, and k, and we sum over I, j, and k. And we need to stick in all the OP coefficients here. So there's a C12I, C3ij, C3jk, and C12k. I'm not being careful about putting the stars in permutations. I'll just drop them. Okay, so, and this is a chiral block, so I'm going to mod square to get the full conformal block. Okay, so these two things are supposed to be equal, and they are equal in the ensemble. They're not, I mean, we can't literally calculate this because we don't exactly know the OP coefficients, but we know how to calculate, we've given a prescription to calculate their averages. So we can calculate the average, well, let me just stick a bar over this equation. We'll calculate the average of G6. Then we'll calculate that average by taking the Gaussian average of the OP coefficients appearing in this sum. And what that Gaussian average does is it contracts these random numbers. So in particular, like we'll get a contraction here that sets I equal to k. So that'll give us a delta ik times C0 squared. And once we've set I equal to k, these two will match up automatically. So these now get a contraction for free. So this one will give us another factor of C0 squared delta ik. The other thing that we do in order to calculate the ensemble average is take the sum over weights and replace it by an integral dhi dhi bar from C over 24 to infinity, weighted by the density of states, the party density of states. So we do that for each of the sums. And that means that this 6-point function here will become G6 average is equal to a bunch of integrals times, I'll just write this schematically. There's a conformal block for 1, 2, 3, 3, 2, 1 odd squared, where now the weights are I, J, and I. And then we have a factor of C0 to the 4th. So what's happened when so by doing the average, what's happened is that we've basically just set the weights equal on the two sides of this diagram. So in the ensemble, this is the only contribution. You might expect that in a individual theory, this will be the leading contribution, and that's true if you assume that the ensemble is self-averaging for this observable. That's really what it's meant. What's meant by saying that it's self-averaging. Okay, so this now I claim is equal to the identity block in the star channel.
Sorry, Tom, I missed that. How do you argue that the Coulomb channel is the dominant one? Can you say again?
Well, we should be able to evaluate this in any channel. And I just picked one, the Coulomb channel, and I want to compare that to the standard answer in holographic theory, which is the star channel, the identity of the star channel. Yeah, this is the Coulomb. Yeah.
Sorry, why can't you just start with this star channel thing and expand it in the Coulomb channel and
You mean by crossing moves? Or
no, well you know the function.
yeah, that's just the reverse of what I'm doing now. So
I see. So
Yeah.
you are saying the main contributions comes from this ensemble element.
no, this is actually an exact equation now. So once we've done the average, and we have this, we now have an integral with these two weights set equal. This is now this is exactly equal to the Virasoro identity block in the dual channel. I haven't finished explaining that. I'm about to explain that.
No, I guess my puzzle is, okay, I know a function, I should be able to expand it
Yes, that's what I'm
in the
doing.
Coulomb channel, and
Yes.
I should know exactly which operator appears and exactly which OP appears.
Yes.
It shouldn't be ensembles.
No, and this is it. This is the math statement. Okay, so the math statement is this: that this expansion in the Coulomb channel is exactly equal to the identity in the star channel. But what I've done here is to give this interpretation in terms of the ensemble average. So the ensemble average is agreeing with the calculation that you're suggesting. That's what I'm saying. To derive, so this is now just a fact about Virasoro blocks. In order to derive this fact, I won't go through the complete derivation, but I'll just sketch how you do this. So you need to do some crossing moves to this 6-point function. Okay, so the first crossing move that you do is you take this internal piece of the 6-point block, and you do a crossing move on that. So when you do that crossing move, you get the 1 and 2 don't the 1, 2 I does not participate, but now this thing goes to the other channel, so we put it that way, and the other one is an I 2, 1, so that also doesn't participate. And the nice thing about crossing transformations is that exactly the same formula that gives you the transformation of the conformal block can be used inside another conformal block. So in this case, we have the sum over heavy operators, J, weighted by C zeros, and the crossing move therefore puts an identity in this in the dual channel. Now you have just half as many integrals left. You have to do a few more crossing moves in order to turn this into that. And I'll skip that. I'll skip those steps, but you just land on exactly the identity block in the star channel. Yeah.
Yeah, I'm a bit confused because now you seem to say that if I had started with ijk instead of iji, you do this crossing move, you project onto the identity, you get your delta ik for free.
But then it wouldn't be weighted by C0 if we had kept all this stuff. It wouldn't be weighted by the correct factors of C0, so you wouldn't get. Yeah. Is there a question about Simone?
Yeah. So yeah, you stress this theory as both a chiral and anti-chiral part in order to apply them. In the statistics, do you vary the chiral C's and the anti-chiral C's independently?
Yes. Yes. Sorry. Wait. The chiral C. Wait. No. The chiral.
You're doing weird contractions for the C's, but then there are C bars. So the C's correlated with the C bar.
There are no C bars. The labels in so the labels here are primaries.
Okay, got it.
But there is a funny thing that's going. So the labels here are primaries. They're not being done with the left and right independently. But once you do the contraction, they become functions of h. They become a function of h times a function of h bar.
Okay.
Yeah.
And that is what allows you to use this.
Exactly. That's what makes it after you use that rule to calculate the average, you now get something that can homomorphically factorize.
Thank you.
Now,
Yeah.
in what sense this was an extra check? Because basically, once you had the check that it worked to cross the identity,
Yeah, I don't think it's
you're just saying that you can cross the identity inside other or
Yeah, I don't think this is really an independent check. This is just sort of consistency. I would say it's just a consistency check. And it's not that it's not that getting the identity implies that gravity is an average or something like that. At this point, this is not a wormhole. This is just an ordinary solution of 3D gravity, and averaging is not required. It just has to be the identity block. I'm just saying it's also consistent with an ensemble average. And when the averaging is really going to become important is when we go to things with multiple boundaries. Yeah.
What happens if we consider the 6-point function identical operator?
Sorry?
If we consider the case when all these operators are identical, so is there some...
All these, you mean the external operators of the identity?
External operators.
Oh, you said are identical.
Yeah.
Well, then we get more contractions. I think it still works, although I don't know if I've worked through the details of that particular case. Then there's a bunch of contractions that we have to worry about in addition to this one, but it's just more complicated, but it'll work out.
There'd be different channels.
Yeah.
So when you do all this contractions, you get 6 times the gravity answer or something? Like,
In this case, no.
you're saying when you do the contractions, you'll just get the star channel by crossing
Do
it?
you mean with identical operators?
No.
No, in this case, you just get the
Is that
star
the
channel.
contraction?
Because the 1 and 2 is the only way you can get this is there's only a single contraction here
Oh, I see.
because you have to set I equal to k. If you had some identical operators, then you'd get those kind of factors, and those would correspond to different ways of different things you could write on the gravity side. Yeah.
I don't know how to properly formulate this, but I'll try. So if I equate the gravity calculation with the ensemble averaging, so postulate that I want this to work, to what extent this equality constrains the average to be given by the mean for fractions?
It requires the, so this requires the Wick contractor. So what this tells you is that in any holographic CFT, forget averaging, this diagonal term is the dominant one.
Do you know the suppression of the subleading term? Just by comparing with the gravity.
It's very suppressed, but no.
1 over S, E minus S.
Well, if you assume no other light states, then it's exponentially suppressed. If you allow for light states that would give you like Witten diagrams like this, then it will only be power law suppressed.
So intuitively, it actually forces you to have weak contraction.
Yes, that's right. The identity, that's kind of the upshot here, is that having the identity in one channel really corresponds to the Gaussian Wick contraction in the dual channel. Those two things are dual to each other. Okay, other questions before we move on?
So this equation holds when you don't have any other operators, right?
Any other
Light operators.
light operators? Yeah, there could. Well, it's always it's the dominant term, even if there is a few other light operators, as long as you don't have a large number of them. It's still the dominant term up to small corrections. Because all these things that I'm writing here are exponential. They're classical in the bulk. They're e to the c type terms, and the corrections you get from other light operators will come in like in the prefactor from Feynman diagrams. Yeah.
Do you know what happens? So if I had another light operator, do I just add another DOZZ C0 times a different random matrix?
Do you mean another like defect type of operator?
Well, if you allow for the exchange of like the first light operator above identity, would you just write, instead of just writing C0, you would write C0 plus C with H, that's the scaling dimension of the light operator?
I don't think it would be that simple, but I don't really know. I don't know. There are some. What we do know how to include, the only correction that we really know how to include here are the corrections from putting. You could also put another defect in one of these, running in one of these. But it turns out what that corresponds to is adding a handle to this geometry, and that allows the defect to run through it. And I'll talk about that later.
Sorry, is it obvious? I mean, how can I see this integral as it's integrated? It's order 0 in large central charge, because the left hand side doesn't have any. It's order 0 in central charge, right?
The left. I'm not sure.
Oh, sorry, the right hand side.
The right hand side is e to the c.
E to the
This is e to the c, or e to the minus c. Yeah. Okay. So that was just a reinterpretation, as I said, of single boundary stuff. You really don't need averaging to get that identity block to work. We don't think that that's how it works. Like in string theory examples where you reduce down to ADS3, I think that's just a fixed, unique CFT. Doesn't have any averaging, but still agrees with that formula. But now we're going to turn to situations where averaging really makes a fundamental difference. And that's if you consider something like 2 copies of the theory, and you calculate some observable, like a correlation function, and look at the connected part. So this is just obviously 0 in a fixed CFT. This is the connected part, but it won't be 0 in an average. So the example that I want to go through is the 4-point function, g to zz bar, times the 4-point function at a different cross ratio. And we're going to average that and just look at the connected part of the average. So to do that calculation, from the CFT side, this is relatively easy. we're going to do it just exactly the same way we just calculated that 6-point function. We just write out the conformal block expansion for these things, and then stick a bar over it. Okay? So let's do that. The conformal block expansion for the 6-point function, sorry, this is, G is the 4-point function, so we get a sum over I of COOI squared times the block squared. That's the first 4-point function. I'll write a Z on there for the kinematics. And then we get another one, sum over J, COOJ squared, J squared, and that one is with cross ratio of Z prime. Okay, so that's just a conformal block expansion in the two channels. Now when we calculate the average, stick a bar over it. And clearly what that average is going to do is it's going to set J equal to I. In other words, calculating the average just picks up the diagonal term in the double conformal block expansion. So this gives us a delta Ij. The other thing that we did, and we're going to do again here, is to replace the sum by an integral over the black hole states. So now we get an integral of just that diagonal term, and that we can write as the square of integral dh, rho 0 of hi, c0 of ho, hi squared times the block, which I'll now write as f of hi z times the block hi z prime, all mod squared. Okay, I skipped one line worth of manipulating that stuff, but this is what you get.
There was a little contraction. I, but that you subtract because you're taking the connector.
That's right.
That was my question.
Yes, yeah, so I'm just taking the ij contraction. Yeah. Okay, so that's sort of the final answer, but we can now do something, notice that something nice happens, which is, remember that this C0 is related to the DOZZ structure constant. And in fact, there were these factors of rho 0 in there. So actually this combination is just C DOZZ of HI squared. Well, let me put the arguments in there. HO, HI squared. The reason there's no factors of the Carty density of states for the light guy is because those are order 1, and we're dropping the non-exponential factors, but you can keep those and you get the correct one-loop stuff as well. Okay, so why is that nice? Well, because now the thing inside here is the Liouville correlation function. That's just the conformal block expansion in Liouville. Because remember, the Liouville CFT only has scalars, so it just has one integral. So you now interpret this as the scalar weight in the Liouville CFT, and this is Liouville. So the answer that we get is the average, I'll just write an equal sign here, equals G Liouville of ZZ prime times the thing with the bars, which is G Liouville of Z bar prime Z bar.
Wasn't the contour different from a Liouville?
This is just the this is just the heavy states, so the contour is the same as the Liouville contour.
You're not including the discrete.
That's right. So at this point, I'm only including the heavy contributions here. The light contributions are subleading, and those are the ones that I mentioned before that we'll come back to. Okay, there's a couple things to note here. First of all, the arguments don't match up on the two sides. Okay, so this is what we started calculating. It has a G of ZZ bar. And the Liouville correlation function that we ended up with has a G of ZZ prime. So that they've gotten mixed up. It's not that, so you have two copies of the CFT. It's not that they each give a Liouville. They are getting correlated by doing the average. And one of the Liouville factors accounts for the left movers in both CFTs, and the other Liouville factor accounts for the right movers in both CFTs. The second thing to note is that this generalizes, in fact, any two-copy observable has this, takes this, this is the answer for anything that you calculate averaging in two copies of the CFT. Like if we calculated a 5-point function at genus 2 times a 5-point function at genus 2, took the average, then we would get a product of two Liouville 5-point functions at genus 2. Really the same argument just goes through. And the last thing I want to note about this equation is that this calculation really did not require a holographic CFT. If we work in the OP limit where z goes to 1 and the Tauberian argument applies to arbitrary CFTs. Okay, so now, if it's not holographic, I don't know what the interpretation is. You can do the calculation. You know, we think that non-holographic CFTs probably obey this Virasoro ETH in the asymptotic regime. And you can write down that ansatz and average over the random matrices, the RIJKs. And this is the answer that you get. And getting this answer did not assume that it was a holographic CFT. It only assumed that we're in a regime where the Tauberian and the Virasoro ETH apply. So there does seem to be some relationship between the asymptotics of CFT and these Liouville correlation functions that goes beyond holography, but I don't really know how to interpret it. So we're just going to stick to the holographic case, but I wanted to mention that.
Sorry.
Yes.
Is this still a non-trivial statement? Meaning there's no, because if I can only process z going to 1 and corresponding for the others, I cannot really write a full PV wheel, right? I would have to write some leading term in PV wheel, and that is not something that, say, factorizes in left and right mover so that in the end there's no average, or like.
I don't think so. Yeah, I think it won't be 0. It won't be 0. So there's some contribution in
So it still says something about average in generic.
It seems to, yes, yes.
Can I ask another question? So does this construction violate the crossing symmetry of CFT? Because now the OP coefficients are random numbers. To get crossing symmetry, you have to know the CIJKs in a very good way. You can, the left-hand side, the right-hand side of crossing can write, but here it's not.
Well, crossing symmetry, as I was saying, is only satisfied on average. It's satisfied after doing the average.
Oh, it's still true.
Yeah.
Maybe the objection would be that the identity block isn't crossing symmetric. It's just that if you average in either channel, you get the same answer.
Well, okay, we have to pick an observable, but like for the 6-point function, the identity block is as crossing symmetric as it needs to be. You know, they're different operators, so it's not supposed to be equal to its crossing. And the statement of crossing symmetry is that you can expand in both channels and get the same answer. So I think it, yeah.
Can I interpret this? Are you saying something like there's a universal level spacing?
I don't know how to, well, no, I don't know how to interpret this. I think it would be very interesting to find some words you can assign to, this is some equation that's true in non-holographic CFTs, but I don't really know what words to assign to it. I would guess, if I had to try to cook something up, I think there should be some regime of the correlation function where you can do some kind of averaging, maybe over Z and Z bar, and that the correlation function in the Tauberian regime, after doing some kind of averaging over the kinematics, is going to be given by Liouville. That's the kind of thing that happens in some other examples that we know of, like the spectral form factor, but it's just a guess. Yes?
I also have a question about the same thing. So, unless we average in a given CFT over Z or something else, for this to be true, we need to define an ensemble of CFTs, right?
Yes, or CFT data, yes.
Right, so if we go outside of holographic regime, so you postulate it, it's essentially a postulate for you that holography gravity is dual to an ensemble of CFTs. You implicitly define it like that, and then you postulate something for this. But once you go outside of holographic regime, then basically you don't know what ensemble you're dealing with. So the statement on the blackboard might never be true because there may be no such ensemble.
That's true, but that's just saying that ETH might be wrong.
No,
I think that
applies to the individual field. Right?
Yes, good. But I think that I agree with what you're saying, but I still think there's content to the statement that if you write down ETH, take the Gaussian average, you get some formula. Now, how to interpret that in an individual CFT that's not holographic, that's, I don't know. But this is what the Gaussian average of the ETH ansatz gives, regardless of whether it's holographic or not.
I understand your statement. You're saying that once I have ETH, I sort of have universality of prediction once I average over the ensemble
Yeah.
field.
Yes.
So you need to be lucky for this ensemble to exist.
We need, yes.
Imagine you have only one non-holographic CFT in the world, and it does satisfy ETH, but it's only one. It's of course
Well,
not true, but it's a...
I think that the situation's a bit better than that. So often when you have when you use ETH, often the ensemble average calculates something in a fixed theory. Even if there's only one example of that theory, it's often true that the ensemble average calculates something in that theory. Maybe it's true here, but I don't know what it calculates in a fixed theory.
If you want to average over Z, I would be with you saying that this is what's it.
Yes, I think you're saying I haven't told you what the interpretation is, and I agree with that. Yes.
But you're suggesting that we could, for example, set Z is equals Z primes and average over some region, and that maybe both sides averages will actually match in one CFT.
I'm saying that would be the thing to try. That would be the thing to try to give an interpretation. Yeah. Okay. So now I want to talk about the wormholes that agree with this calculation. So there is, of course, a long history of matching solutions of the Bootstrap to gravitational physics in ADS. Most of that has been done perturbatively around the vacuum state. There's some work that does it perturbatively around the thermal state. But ultimately, in order to compare Bootstrap to gravity, we should be able to work in any gravitational background. And there's the factorization puzzle here is important. You know, any gravitational background includes these non-factorizing wormhole type solutions. Einstein gravity plus matter very generically has these solutions. And so we should try to understand them from the Bootstrap point of view. In 3 dimensions, there's a wormhole that as far as I know, was first discussed by Madison and Maus. There's a whole class of these wormholes. One of them, to illustrate, is a three-dimensional geometry, a Euclidean 3 geometry, which has the topology of a genus 2 Riemann surface times an interval. The metric is d rho squared plus cosh squared rho d sigma squared. And in fact, in order for this to be to satisfy the Einstein equations in 3 dimensions, all you need is for this Riemann surface to be hyperbolic. So this is a hyperbolic 2-manifold. So given any hyperbolic 2-manifold, you can construct one of these solutions basically by multiplying it by an interval and sticking in this Koch. According to the usual dictionary, this should contribute to the product of 2 genus 2 partition functions. Because what does the dictionary tell us? It tells us to calculate this product. We should study gravity with the boundary conditions, which are 2 genus 2s, and then do the gravitational path integral, fill it in every way that gravity allows us. So this is the factorization puzzle in this context. And there's a whole family of wormholes like this, because you can construct lots of hyperbolic 2 manifolds either by taking stuff like this as higher genus, or by inserting particles that travel between the 2 sides. So you can generalize this to include matter by inserting stuff that goes across the wormhole. And the claim is that these multi-boundary solutions agree with the predictions of the large C ensemble that I have defined. So, for example, the simplest hyperbolic 2 manifold is a sphere with 3 punctures. So, the simplest one of these wormholes has the topology of a sphere times an interval, but with 3 defects on the sphere. So this would contribute, by the usual dictionary, to O1, O2, O3 squared. To construct this wormhole, we're going to just take this ansatz. We know that's a hyperbolic 2 manifold, so I'm going to write it as d rho squared plus cosh squared rho e to the phi of zz bar times dz bar. This is an ansatz for the metric. Then the Einstein equations, so now we take this ansatz and we plug it into the Einstein equations. As I said, as long as the Einstein equations just tell you that the metric here has to be hyperbolic, and the equation that says that this metric is hyperbolic is the Liouville equation. So the Einstein equation becomes the Liouville equation. That is d bar phi is equal to 1/2 phi. But there are sources, and those give you a term 4 pi g, sum over the defects of delta z minus ci. Okay, so it's a Liouville equation with sources. From the point of view of the bulk theory, those just come from including those wormline actions for the particles in bulk.
Sorry, Tom.
Yes.
Are these like parabolic or elliptic singularities?
These are elliptic. Maybe you can do parabolic too, but these are elliptic. Okay, so this is the solution. And we're not going to need you can solve this equation actually in 3 defects, but we're not going to need it. So now you take this and plug it in to the bulk action to calculate the action of the wormhole. So in order to calculate the action of the wormhole, what you need to do is you need to put a cutoff here near the boundary on each side, and then calculate that action, including all the boundary terms and counter terms, etc. There's a standard procedure that you have to go through, which I'm not going to do, but you end up with the regulated volume of that hyperbolic 3 manifold, which is the volume minus 1/2 the area. The epsilon indicates that there's a cutoff. Since there are these matter terms, you also have to add some defect counter terms to make everything finite. And once you do that, you get a Liouville action with defects, up to some normalization terms that are important but annoying to keep track of. So after normalizing everything, it agrees with Liouville. And in particular, e to the minus s of this 3-point wormhole that's drawn there gives you exactly the universal OPE function C0 squared. This is if we set the 3 points at the canonical locations, 0, 1, and infinity.
Here in the delta functions, you make also some eta i's for the strength of the delta function.
Yeah, I should have I can't remember if it's, yeah, I think it's just eta I. Yeah. Okay, so let me recap. There's this on-shell solution of 3D gravity with 3 defects, and the on-shell action, contribution of the path integral, is just a universal 3-point function C0 squared. And that is the average 3-point function in the ensemble. So this is an agreement between the ensemble average 3-point function and the bulk wormhole with 3 defects. Just a remark is that although we put a hyperbolic metric on this sphere, we're interested in studying the CFT on a flat metric. All the results that I'm talking about are for the CFT on a flat metric. So in order to undo that, you have to use a weakly cutoff for the conformal fit. You have to choose the cutoff here in ADS3 in such a way that it cancels off the Liouville factor and puts a flat metric on the boundary. So I won't go through that, but we're always studying the CFT in flat space.
Sorry, Tom, small question. You have 2 sets of independent conformal transformations that act on the boundaries?
Yes. Yes, that's right.
Is it obvious the symmetry in the bound?
think it's obvious, but it's true. Maybe it's obvious, at least in 3 dimensions, because the stress tensor is determined by Pfefferman-Graham. So the stress tensor is really just something that's determined locally near the boundary. So maybe there's a way to make it obvious using that fact. Okay, I'm just going to take another couple minutes to finish up the more general wormholes. So for a general two-boundary calculation would be something like some crazy higher genus thing with a bunch of defects running across it. And moreover, we could put different moduli on the two sides of the wormhole. So I'll call them Z and Z bar, but I really mean all of the cross ratios as well as all the complex structure moduli of that Riemann surface. And on the left, we have Z prime and Z bar prime. Okay, so there are manifolds that look like this. In general, you can't write down their metric, but you can write it down. Well, if these moduli are similar enough, there's a finite regime of moduli space in which Z is similar to Z prime, in which you can write down the metric. And that's a regime that's been studied by mathematicians, and everything can be done in great detail. For the more general case, you have to be a little bit more indirect, but you can still calculate the action. And again, the result is e to the minus s wormhole is G Liouville of ZZ prime, G Liouville of Z bar prime, Z bar. It's the product. So again, it reduces to a Liouville-like action. It's not the ordinary Liouville action because it's correlating the two sides. It's that you end up correlating the two sides because you have the modulus Z is paired with Z prime. And the upshot is that this is exactly what we got from the ensemble by averaging the product of two observables in the two copies of the CFT.
Question. So the left of this Liouville depends on the morphically of the moduli of the two Riemann surfaces? Or
Sorry, what does?
like if you have the modulus tau or Hilbert matrix.
Yeah.
The left factor depends on morphically on that, and the right
Yeah, so this one would have a
like tau.
this one would have a tau
And tau prime.
tau prime. Exactly. Yeah.
And then the bars.
Yeah, I think for the with the usual conventions, you actually need a minus tau prime here because that needs to have negative imaginary part. But yeah. Okay.
Sorry,
Yes.
just like for the wormhole action, you've already integrated out all the coordinates, right? But on the other side, you have Z bar, Z prime, Z prime.
These coordinates are the coordinates of. Sorry. Maybe I should have given this a different name. Yeah, I reused the variable Z. Okay, so I should have given this a different name. These Z and Z bar denote the insertion points of the operators at the boundary. So these are true parameters. These are the parameters in the correlation function that we're calculating. And I didn't mean to give it the same name as the bulk coordinate.
Okay.
So the conjecture, in general, is that the bulk saddles of 3D gravity plus particles are in one-to-one correspondence with the large C ensemble, in the sense that in this ensemble, if you pick a channel to expand your correlation functions, and then you calculate the average in that channel, in general there can be many different OPE contractions, say of a complicated observable, in your choice of channel. And basically the conjecture is that each of those corresponds to a bulk set. And that as you continue this procedure at more and more complicated observables, and even with more and more conformal boundaries and more copies of the CFT, that there should be a way of matching those contributions to the average saddle by saddle to the contributions in the bulk. And what this really means for the theory of quantum 3D gravity is a bit less clear, because presumably in that theory we're supposed to sum over all the saddles. Those sums are notoriously difficult and probably even UV sensitive. So in other words, the contributions of off-shell path integral are of similar size to the contributions that you get by summing over all the subleading saddle lengths. So how to do those sums and how to really organize this and make sense of the full non-perturbative quantum theory is still an open question. But at least saddle by saddle, there are many examples where this works, and it would be really nice to prove this and to find the exact statement. It needs to involve some kind of recursive procedure where you gradually solve more and more bootstrap equations on the boundary side, and you gradually include higher and higher topologies on the bulk side. Okay, let's stop there for today.
What if your two boundaries are each a torus?
So in order to get a hyperbolic two-manifold, you can have a sphere with 3 or more points, or a torus with 1 or more points.
What if they're a torus with 0 points?
A torus with 0 points is not hyperbolic,
I know that.
and so there is no, so there's no saddle like this. Now, that doesn't mean it doesn't contribute necessarily, but it means you have to do something more elaborate. Okay, so one thing you could try to do is you could try to do the off-shell gravitational path integral with the double torus boundary conditions. There's a proposal for how to do this by Kotler and Jensen, basically using the method of constrained instantons. They first constrain the size at the middle of the wormhole, and then you find a saddle, and then you integrate over the size, integrate over that constraint. That gives an answer for the double partition function that, at least in some limits, appears to be consistent with eigenvalue repulsion in random matrix theory. Another thing that you can do, also Kotler and Jensen, is to study the gravitational path integral with some modified boundary conditions. So it's not the usual ensemble where it's just z times z, but it's some more elaborate choice of boundary conditions that correlates the two sides, and then you can get this thing to be a saddle and interpret it that way.
I think it's the same answer, because you have something that seems to be what makes them clear, right? It's a Neuville answer. You get some answer from Neuville theory for all hyperbolic manifolds, but maybe not for the others.
Yeah, there is, so this claim about Neuville only applies to the hyperbolic case, and we have not found a way of taking the, so you could try to take the 1-point function on the torus and then like take away the point, or send its weight to 0 or something. When you do that, it diverges, and we haven't managed to make sense of it. You might hope that that would give you back the double torus, but we don't know how to do it. The same is also true in 2D gravity, that you can't get the ZZ by taking the limit of the double 1-point function. You just don't know. Yeah.
Yeah, I also wonder about the physical radius of this wormhole. So like in the 3-point G0 case, what sets the middle radius? So how related to the dimension dimension of the scaling dimension of the things you took on the outside?
I think that's just a normalization. And in the Liouville language, that becomes the Liouville cosmological constant. So the Liouville cosmological constant it sets some normalization, and that will give the minimal size of the in the
But
3-point
that's
function.
a meaningful thing, right? In ADS units, the size of the radius of the wormhole in ADS units is a meaningful quantity, right? The bottom. That's a convention dependent one.
Well, that's only true if it's a, I mean, remember that term in the metric was like e to the phi dz squared, and dz squared is the plane. So I don't, I mean, what do you mean by the size? This is the metric on the so if we take the 3-point wormhole and cut it down the middle, this is the metric on that cut. So what size do you want to say this is? You want to calculate the volume of that?
The phi. So, I mean, you have a point at
But I think that- I think
at
that's-
0 and a point at 1. So I guess.
Well, you can put the points wherever you want, and then you can rescale z. So I think that just will enter into the normalization of the cosmological constant.
You can compute the geodesic length from.
There's no geodesic on the 3-punctured sphere. There's another quantity that's very interesting that you can calculate, which has a meaning, and that would be if say we take a 4-point function and we cut the 4-point function. Now the 4-punctured sphere does have a minimal geodesic at the center, so there'll be a geodesic like here.
Yes.
And the length of that geodesic is meaningful, and that corresponds to the dimension of the operator running in the intermediate channel in this 4-point function. That's what sets that one. The 3-point function, I don't think that there's.
I mean, you can calculate the curvature.
In JT gravity, there is a meaningful parameter, which is the length or width of the wormhole. But that's because you have dilaton and you cut off the boundary, right? So the length of the boundary is meaningful. And in 3D, you don't have an available.
But can you calculate the Riemann tensor that is placed on this surface in the middle?
Well, yeah, but it's a tensor, and there's z's here. I don't see any way to get a natural normalization for the.
Sorry, but the 3-punctured sphere has a finite volume, no? Like in a hyperbolic metric with elliptic singularities. I think it has a finite area, sorry.
It does, but I think the normalization.
Like this e to the phi dz squared is integrated over R2.
I can shift this phi. Yes, it has a volume, but
I don't think so.
well, shifting the phi shifts the Liouville cosmological constant.
Yeah.
Yes. So that's
Well, that's the ADS radius, right? The actual cosmological constant.
yes, that's right. Yeah.
So you get the natural volume for this 3-punctured sphere in units of the ADS radius.
Okay, that sounds right. Yeah, that sounds right. Yeah.
I was confused about this conjecture. You had Bootstrap channel and Euclidean contraction, I guess. So, what did you mean by the Bootstrap? Are we supposed to, if I do some crossing on this channel, am I supposed to get a sum over saddles? How should I be thinking about the fact that I have to sum over the saddles?
Yeah, so I glossed over something important, which is that when we derived the C0 formula, we picked the identity in a particular channel. Okay, so you pick the identity in some channel and you derive the C0s. Now, if you say you braid 2 operators, if you braid 2 operators, then you'll pick up non-perturbative corrections to the C0 formula from the identity in some braided channel. So there are other channels like that contribute, and those could, depending where you are in moduli space, so depending where you are in tight Miller space, I should say, really. Different channels can dominate, and you have to pick the one that dominates.
Sorry. So now the external operators are defects. How about if it's a usual light operators?
So if you want the, okay, so the external operators are defects, just meaning that there's massive particles in the bowl. The nice thing about that is that you can talk about solutions of the Einstein equations instead of Witten diagrams. Now, we've also checked the one loop corrections to this, and so my feeling is that if you, so I think it's probably true that you could get the same thing to work with light fields, but it's just going to be more complicated because then you have to calculate a bunch of Witten diagrams instead of just keeping track of the exponential factors and the one loop corrections. But I imagine that there's probably a way to
numerically solve the Einstein equation with that.
Yeah, it was really just simplicity for the first step. I would guess it can be done, but we don't know how to in detail.
Okay, so we are a bit over time, so let's find some